All right, thank you very much for the introduction. Good morning, everyone. My name is Yue. I'm an associate professor at the University of Virginia. I'll be presenting FLEX, fast, accurate DNN inference for low overhead edges using heterogeneous accelerator execution. I'm presenting on behalf of my colleagues, Tanmoy, Haiying, and Anand. Tanmoy is currently a postdoc at UVA. This is joint work between UVA and Georgia Tech. So in recent years, ML inference has increasingly shifted to edge devices. There's a need for fast, accurate, and energy-efficient execution. Modern edge devices, including flagship Android and Apple smartphones and tablets, are equipped with GPUs that can significantly accelerate machine learning tasks. To conserve power, these devices often employ low-precision quantization methods. Moreover, a large portion of users rely on low-cost edge devices, especially in regions where high-end devices are prohibitively expensive. For example, as of January 2023, around 70% of the smartphone users in Africa, Asia, and South Africa, they use low-cost Android devices. These edge devices often rely on low-cost accelerators, or LCAs for short, like NPUs, DSPs, or TPUs that use reduced precision, for example, int8 or epi16, in order to save power. The reduction in precision can lead to significant accuracy degradation. So here's a visual example that highlights this problem. So when all layers are executed on CPU, we achieve the correct classification. So in this case, identifying this image as a cat with high confidence of 78%. However, when the same model is running entirely on the LCA, the classification shifts to an inaccurate label, which is a fox, with low confidence. So the goal of this work is to assign layers across CPU and LCA in order to meet the timeliness and accuracy requirements. So the machine learning-based model partitioning algorithm, or what is called MLMP, is a static model partitioning method that uses heuristic to either maximize accuracy, which is MLMPA, the heuristic for maximizing accuracy, or to minimize latency, MLMPT, the heuristic for minimizing the time. So it applies a greedy one-size-fits-all strategy, but often misses better per input solutions. So this drawback is also confirmed by our experiment. The figure shows the number of incorrect decisions made by each method compared to the oracle across various models. What is oracle? Oracle is obtained by exhaustively enumerating all the possible layer assignments in order to find the optimal schedule that meets the accuracy guarantee, which is producing the same output label as running all layers on CPU, while at the same time minimizing the inference time. In addition to Oracle and MLMP, we also propose a simple input method, input-aware method. It progressively moves layers to the LCA, starting from the end of the DNN model, until the accuracy guarantee is violated. We then randomly select the valid assignment from those that satisfy this guarantee. MLMPA and MLMPT make significantly more incorrect decisions, with errors rates nearly 2 times higher than the input-aware method. In contrast, the input-aware method incurs only about 2.5% more errors compared to the oracle. So to summarize, the static approach doesn't account for the input characteristics, which leads to unnecessary accuracy loss. So the key insight of this work is that accuracy can be preserved if layer assignments are adjusted dynamically based on the input characteristics. To this end, we propose FLEX to make input-aware decisions. In addition to MLMP, several other prior works have explored partitioning or adapting DNN models for efficient inference. Prior works like Alert and Mystify, they select from pre-trained models but don't support per-layer scheduling. Another work, AMPT, improves training through mixed precision but doesn't adapt at the inference time dynamically. In contrast, Flex is the first system to perform dynamic per input layer assignment across CPU and LCA, combining the benefits of both low latency execution and high accuracy. So to guide Flex design, we first analyze the performance of individual layers on different hardware accelerators. This figure presents the results, showing the reduction ratio when a single layer runs on the LCA while the others run on CPU. We observe that the so-called heavy hitter layers yield higher reduction in inference time and accuracy when executed on LCA compared to CPU. Therefore, these layers should run on LCAs when their output match the input. Otherwise, they should remain on CPU. So what is heavy hit layers? The hitter layers mean layers that contribute significantly to both inference time reduction and the accuracy degradation when offloaded to the LCA. So next, we compare different division point layers and run this layer and its preceding layers on the CPU and run its succeeding layers on the LCA. The first figure on the left-hand side, it shows the inference time and accuracy for each division point layer for each input. So what's the observation? We observe that the accuracy and time savings on LCAs improve as the division point moves from the first to the last layer of the DNN, despite some exceptions. The figure on the right-hand side shows the save time compared to running all the layers on CPU per input at each division point. There's a non-negligible communication cost when layers are split across CPU and LCA. Sometimes this overhead can outweigh the speed-up gain from the LCA itself. And therefore, the takeaway from this experiment is that in order to minimize the inference time, which includes communication overhead, while maximizing the accuracy, the division point should balance the computation and the communication trade-offs. So Flex addresses all these limitations of static partitioning by making dynamic input-aware layer assignments across CPU and LCA. It includes three methods. The first method is a per-layer heuristic. The second method is a model-driven heuristic, and the third method is a reinforcement learning-based method. Flex uses these offline trained models to make fast per input decisions. As shown in this figure, it takes three steps. First, an input arrives at the system, and then Flex determines the layer assignment dynamically. It then loads the layer across CPU and LCA, and finally, it executes the inference. And we'll cover the design of each and every method next. So our design begins with the offline profiling, where we collect performance and accuracy metrics for each layer. We train two regressors offline, RFT and RFA, to estimate the inference time and accuracy of each layer. During inference, Flex first checks whether the CPU and LCA output match. If yes, we move those layers to LCA. Otherwise, we only move them if the accuracy constraints is still satisfied. So let's next see the heuristic in detail. So in the heuristic for individual layer assignment, we first allocate all the layers to the CPU to preserve accuracy. So when a new input arrives, Flex begins the assignment. So first, Flex evaluates each layer to determine whether running it on the LCA produces the same output as the CPU. Layers with matching output are marked as a green color. They are safe to be moved to the LCA. Among the matched layers, Flex compute a ratio of time reduction to the accuracy loss for each layer, which is a ratio shown at the bottom of the slide. It then prioritizes the matched layer with higher ratios to be moved to the LCA until the timeliness requirement is satisfied. These layers offer higher inference time reduction, but with low accuracy loss. So after all the matched layers are moved to the LCA, if the timeliness requirement is still not satisfied, the unmatched layers, which is colored in yellow, will be moved to LCA using the same approach. During this process, we use a pre-trained regression model, RFT, for estimating the time, and uses RFA for estimating the accuracy. However, as you can see, such per layer assignment guarantee, even though it incurs high overhead, which can be up to 70 milliseconds. So to address this overhead, we aim to find a single division point between CPU and LCA instead of evaluating every layer. If the user prioritizes accuracy, we move shallow layers in groups to LCA and refine once the latency constraint is satisfied. If the priority is timeliness, which is latency, we move the heavy layers from the end of the model to LCA, as long as the accuracy and the memory constraints are met. We also use a model classifier to judge if the CPU and LCA output match. If yes, we move layers more aggressively. To speed things up, we apply binary search based on the observation that latency and accuracy change mostly monotonically as layers shift. We begin with the deep neural net composed of sequential layers from layer 1 all the way to layer 28. By default, we assign all layers to the CPU to preserve accuracy. To reduce the runtime overhead, Flex doesn't evaluate each individual layer. Instead, it first divides the model into equal-sized groups of m layers. The binary search starts by evaluating the middle group, which in this case is group 4. Flex simulates what happens if all layers from this group and onward are assigned to LCA, while the earlier layers stay on CPU. Flex uses RFT and RFA to estimate the latency saved and the accuracy loss if the group and beyond are offloaded to LCA. If the accuracy constraint is satisfied, Flex continues its binary search onward toward the left half of the model to see if we can offload even more layers to LCA to maximize the save time. If the accuracy constraint is not satisfied, Flex continues a binary search towards the right half of the model to meet the accuracy constraint. The same evaluation is repeated until the group with the best save time while satisfying the accuracy constraint is found. Once Flex identifies the best group, it zooms in and performs a linear search within that particular group to find the optimal division point. So while the heuristic works well, it adds overhead. We reduce this overhead by using a reinforcement learning-based method trained with soft actor critic, SAC, and curriculum learning. In curriculum learning, training data is presented in a structured order from simpler to more complex models. The RL policy learns to make fast input-aware decisions while meeting accuracy and latency constraints. The RL agent takes in system constraint, for example, time, memory, and accuracy, and decides per layer assignment, for example, 0 for CPU and 1 for LCA. And the agent is trained to satisfy the latency and accuracy constraints, guided by a reward function that penalizes violation and favors efficient assignments. For evaluation, we test Flex on 3 real edge devices. We run different vision NLP and time series models on the ImageNet dataset, HAR dataset, and SQuAD dataset. The input arrives using a Poisson distribution with a mean interval time of 3 seconds. Besides the mentioned methods in Reddit works, we compare Flex with the strawman and Oracle. The strawman heuristic moves layers from the N to the LCA until the accuracy and time requirement are satisfied. Oracle enumerates all these possible layers assignments in order to achieve the optimal accuracy with optimal inference time. We also created the following variants of Flex for comparison, namely Flex L, Flex D, Flex B, Flex RL, and Flex RL+. First, we quantify the timeliness guarantee. Flex significantly improves the timeliness guarantee over prior methods. By incorporating input awareness and input layer placement, Flex D, Flex B, and Flex L outperform MLMP baseline by up to 38%. Further, the reinforcement learning-based method boosts the performance even more, enabling FlexRL Plus to achieve timeliness within 3.5% of the oracle, despite being fully online and lightweight. Next, we evaluate the accuracy guarantee. FlexD and FlexB outperform MLMP baselines by up to 27% thanks to the input awareness. FlexL and FlexRL Plus further refine accuracy, with FlexRL Plus achieving results within 2.5% of oracle while remaining fully online. And finally, we quantify the computational overhead of each method. The overhead measures the time from when the input arrives at the system to when the input starts the processing. FlexD has 48% lower computation overhead than FlexL due to finding one division point instead of individual layer assignments. FlexB improves FlexD by 41% by using binary search instead of linear search. And FlexRL Plus improves FlexB by 90% by using RL. And FlexRL Plus and both FlexRL show similar performance when using the same RL method. To summarize, Flex is the first system to enable dynamic layer assignment for DNN inference on mobile LCAs. It uses a combination of machine learning-based heuristics and RL, reinforcement learning, in order to meet both the latency and accuracy goals. Future works include the scaling to multiple accelerators setup and further reduce the decision overhead. With that, I conclude my talk. I may not be the best person to handle questions, but I will try my best.